we've done some examples. So now what we're going to do is talk about a few properties of Nash equilibrium, do a couple of definitions, and then we'll use those properties and definitions in order to solve the 3x3 rock, paper, scissors game. Okay, so let's start with some properties. Or no, let's start with the definition. So you guys remember what a symmetric Nash equilibrium is? So let's start here with what you might remember. A star is a symmetric Nash equilibrium if and only if a 1 star equals a 2 star. A star has to be a Nash equilibrium already. And a I star equals a J star for all I j. Okay. Now, what is a symmetric mixed strategy Nash equilibrium? Now, in a mixed strategy Nash equilibrium, you are choosing, every player is choosing a particular mix over different actions, right? So alpha star is a symmetric MSNE if and only if you do need the action sets to be the same. So A1 star should equal A2 star, or AI star should equal AJ star for all IJ. And I'm going to fix it up there as well for all IJ. And alpha star itself should be a mixed strategy Nash equilibrium. And the probability with which an action, let's call it X, is chosen according to alpha I star should be the same as the probability with which an action X is chosen according to alpha J star for all actions available to players. Okay. What does this last thing mean? So if we're talking about a game like rock, paper, scissors, a symmetric mixed strategy Nash equilibrium is one in which either player is choosing rock with the same probability. So the probability with which player 1 chooses rock has to be the same as the probability with which player 2 chooses rock. The probability with which player 1 chooses scissors has to be the same as the probability with which player 2 chooses scissors. And the probability with which player 3 chooses, player 1 chooses paper should be the same as the probability with which player 2 chooses paper. So each action has to be chosen by the same, with the same probability by both players. Right, just to give you a more concrete example, here, the probability with which player 1 chooses T according to alpha 1 star is going to be 1/2, right? Because P star, remember, is 1/2. Okay, so I trust that you remember that P star equals 1/2 is something that we showed here when we found this MSNE. Okay, and so all this means is that in that equilibrium, player 1 chooses T with probability 1/2. Okay, and according to this symmetry property, the probability with which any action X is chosen in equilibrium by player I should be the same as the probability that the same action X is chosen by a different player J. And this has to hold true for all the actions available to both players and for all players in this game. So I also need another for all I J. Okay? And that is a symmetric mixed strategy Nash equilibrium. Okay. Um, let's talk about strict and weak dominance in the case of mixed strategy Nash equilibrium. So you remember this thing for actions? So an action, let's start with for player I. It's always defined for a particular player. For player I, an action AI strictly dominates AI prime if and only if the utility that player I gets from choosing the action AI when other players choose A minus I is strictly greater than the utility that player I gets from choosing AI prime when other players choose A minus I. And if this holds true for all A minus I, then we are good. Okay, so this needs to hold for all AI. But this is with pure strategies. With mixed strategies, the thing that changes is now we're talking about a mix over actions or a mixed action, which is alpha I strictly dominates alpha I prime if the expected utility that player I gets from choosing alpha I is strictly greater than the expected utility that player I gets from choosing alpha I prime when other players choose A minus I. And you only need to test it for actions of other players, not over mixes over actions. Because if it's true for every possible combination of actions that those other players can possibly take, then this will also hold for every possible mix over those actions that those other players could possibly take. So if alpha I is better than alpha I prime for every possible action combination for other players, then it's also going to be true for every possible mix over actions that other players could take. And so this is just simpler to check. And then similarly, weak domination looks like this. For the I, a mix over actions, alpha I weakly dominates alpha I prime if and only if the expected utility that player I gets from alpha I given alpha A minus I is weakly greater than the expected utility that player I gets from choosing alpha I prime given A minus I for all A minus I, and the expected utility that player I gets from choosing alpha I given A minus I is strictly greater than the expected utility that player I gets from choosing alpha I prime A minus I. Okay, so very similar to weak domination in the case of actions. You need a weak inequality to hold for all possible action combinations that the other player could take. And you need to have a strict inequality in at least one situation. So in at least one situation, alpha I should be superior to alpha I prime. Okay, so that's strict and weak domination. That is symmetry. Um, let's talk about this. Why is this helpful? It's helpful because if alpha I strictly dominates alpha I prime, then alpha I prime cannot be chosen in any MSNE. Okay, let's call this result 1 today. We can go finer than this. Let's, okay, R2 is result 2. If AI strictly dominates AI prime, then for any MSNE alpha star, so suppose alpha star is a mixed strategy Nash equilibrium, the probability with which AI prime is chosen according to alpha I star has to be equal to 0. Right? So what this says is that if there is an action that is strictly dominated, so AI prime is strictly dominated by AI, then for any equilibrium, so if alpha star is a mixed strategy Nash equilibrium, it has to be that the probability that AI prime, the strictly dominated action, will not be played with positive probability. You will not choose that action in equilibrium. Okay. Um, let's do more. Let's talk about existence. Result 3. If you have finite action sets, means that the set of actions is finite, so it cannot be like the Cournot game where you can choose any continuous number of actions. It should be something like rock, paper, scissors, right? Where you can write down how many actions there are. Or tic-tac-toe. You only have a finite number of options at any given time. If you have finite action sets, finite number of players, then there exists an MSNE. Right? This is not true for pure strategy Nash equilibria. We can write out games in which pure strategy Nash equilibria do not exist. But a mixed strategy Nash equilibrium, if you're writing a payoff matrix, has to exist. Because if you've got a payoff matrix there, then it has to be finite actions. Otherwise, you don't have a payoff matrix. And, well, two players, which is finite. Otherwise, you don't have a matrix. Um, so as soon as you have finite action sets for finite players, you have to have at least one mixed strategy Nash equilibrium. I won't go into the proof of this. This is just a simple fixed point theorem. Um, but for our undergraduate course, it's sufficient to know that this result exists. Okay. But we can do one better. We can do, let's call this result 4. And we can say that with the same conditions, if action sets are finite and we have finite number of players, then there exists an MSNE in which no player chooses a weakly dominated mixed strategy. Right? So alpha I prime is not weakly dominated. Alpha I star is not weakly dominated for any I in according to this. So with the same preconditions, you can have a more powerful result. Okay. What else? What else? Um, let's do another one. Let's add one more condition. If action sets are finite players, and symmetric game, then there exists a symmetric MSNE. Okay. And we know what a symmetric mixed strategy Nash equilibrium is because I just defined it. And what else? You know this already from the examples that we did earlier, but might as well write it out formally. And this is, suppose alpha star is a mixed strategy Nash equilibrium. Suppose the probability with which player I chooses AI given alpha I star is positive, and probability with which player I chooses AI prime, just a different action available to player I, according to alpha I star, is also positive. So there are two actions that player one is choosing with positive probability. Then it must be that the expected utility that player I gets from choosing the action AI when other players are choosing alpha minus I star, so they're mixing according to their equilibrium strategy, has to equal the expected utility that player I gets from choosing AI prime given alpha minus I star. Right? So this is the same as what we were talking about earlier, where we said that player 2 is choosing to mix in a way that leaves player 1 just indifferent between choosing top and bottom. And player 1 is choosing to mix between top and bottom in a way that leaves player 2 just indifferent between their two actions. Okay, so I'll pause here, otherwise this becomes a very long video. And then when I come back, we can talk about how we're going to use all of these new results in order to find equilibrium in a simple rock, paper, scissors game that you all know and love.